All right, our second review session. So, like I said, last time we finished up with converting our definite integrals into a limit and a summation, which is commonly in the multiple choice. Today, we're going to just pick up with integrals in general. So we know what an integral does, right? An integral just tells us if we've got some function from a to b, the integral of f of x from a to b dx is just the area underneath that curve. And we got to be careful when we say it's the area underneath the curve, because really, if that function is above the x-axis, it's the area underneath the curve. But if that function is below the x-axis, right, this integral, call this g, the integral from a to b of g of x dx is actually the opposite of the area underneath the curve, right? It's a negative value. And so we just want to make sure that we're careful about that when we're asked to find area, to recognize that the integral itself is positive above the x-axis, but negative when the function is below the x-axis. So if a question asks you about area and you know that the region is entirely below the x-axis, just take the opposite of the integral. If it's always above the x-axis, then just take the integral. If the function happens to cross through the x-axis from a to b, right? We'll call this point C where it intersects. In order to find the area of this one, we need to remember that it's the integral from a to c of h of x. And since that one's below, we take the opposite of that one. And then we add to that the integral from c to b of h of x, and that one's positive because it's above. So just remember that you got to find those places where the function crosses through the x-axis if you're specifically talking about area. Everybody good with that?
Makes sense.
Yeah.
Wonderful. Okay. So how do we integrate? Well, normally our first thing to go to is the power rule. Right, and I'm not going to go through with how to integrate using the power rule because that's pretty straightforward, right? You just go up one power and then divide by that new power, right? I mean, I'll just, if we have x squared dx, right, you should, I don't know how you would have made it this far in the class without being able to get x cubed over 3 plus a constant. On the free response, don't forget plus a constant, okay? Make sure you put your plus a constant. Okay. If it's a definite integral, right, we remember that, what do we need to do? So let's make it x squared again. We integrate, and we evaluate from the upper limit, 8/3, minus the lower limit, 1/3, to give us 7/3, right? So if it's an indefinite integral, plus a constant. If it's a definite integral, evaluate it at the upper limit, evaluate it at the lower limit, and get your value, right? Now, all of these ones that are just polynomials or powers of like x to the 2/3 are all easy to use using the power rule. All the things we could use power rule for with derivatives, you can use it for with integrals. So this one would just become 3/5 x to the 5/3 plus our constant. There we go, up to 5/3, divide by 5/3 means multiply by 3/5. Okay. And then there's all the rules that you just need to know that are all over those integral rule sheets that I gave you. For example, the integral of 1 over x dx, we want to remember is natural log absolute value of x plus a constant. Now, I want to specifically talk about this one because this is one that gets commonly screwed up on the AP test by students. If I have this integral, a common mistake is for people to say, this is not correct, we're going to say does not equal this. Right? That is not true. Right? This thing in the denominator has to just be a single variable down here in order for us to integrate it to become natural log of the absolute value of that variable. This should be the integral of x to the -2 dx, which this will use the power rule on. We'll go up to -1 and divide by a -1. or have negative 1 over x plus our constant. Everybody good with that?
Yes.
Okay, that's very important. A lot of people screw integrals like that up. They'll see something like, and even in the differential equations, let's say, suppose you were trying to integrate dx over 3 minus x. Well, a lot of people look at that and say, okay, that's just some function down here below the dx. So we integrate that to get natural log absolute value 3 minus x plus a constant. But no, it is not that. Okay, it is not that. You have to do the U substitution. So now we'll start talking about a U substitution. The U substitution allows you to do the chain rule for derivatives in reverse with integrals. So we find the complicated piece of the function, so in this case, the 3 minus x, that is causing difficulty. So we can't just do this rule. But if it was just a u down here, if u was 3 minus x, and we had du over u, then we could use that rule. So we have to let u equal 3 minus x, giving us du equals negative 1 dx, right? If you take the derivative of 3 minus x, that gives you negative 1 dx. So we put in a negative sign up here to make it a negative 1 dx, and we put a negative sign outside to cancel those things out, and we end up with the opposite of the integral of du over u. And that, now you can use that rule, becomes negative natural log absolute value of u plus your constant. And then after that, you just replace the u with your 3 minus x and get negative natural log absolute value of 3 minus x plus a constant. Everybody good with that?
Yep.
All right. Yeah, so I would say that this mistake with integration is probably the most common mistake that people make on the AP test. And it usually shows up when they're in differential equations. So, you know, some of the differential equation problems that we've seen give you something often like dy dx equals something like x y squared. And so when you separate your variables, people are very tempted to just make this natural log absolute value y squared, but it is not, right? It's just negative 1 over y when you do the power rule, right? And then you'd solve for y. Or it shows up in the ones where they give you something like dw dt equals 1/5 of 700 minus w. And when you separate the variables, you get this. And then you have to do the u sub on the 700 minus w to get the natural log, right? U equals 700 minus w, just like we did with the last one. Du equals negative dw. So as we integrate, we put negatives inside and outside to get negative integral du over u. Everybody good with that? I know I'm spending a lot of time on that specific one, but I found over the years that that's one of the biggest mistakes that people make. So.
Yeah, that makes sense. The second one you showed us reminds me of the baby bird problem. I've seen that one way too many times, like while I've been studying the baby bird problem.
Yes, the baby bird, it's the potato and the trash. The potato, baby bird, and the trash problems. Those are, yes. So hopefully when you get a baby bird, potato, or trash problem on the AP test, you will correctly integrate. That would be good.
Hopefully.
All right, so let's see, I got all sidetracked. Okay, so we were talking about U substitutions, right? So when we talk about U substitutions, we can use them anytime the integral, well, not anytime, but a lot of times when the integral is something that's a function within a function, right? So if I have something like integral of the sine of 7x dx, because this is the sine of a function, you can't just integrate it and say that's negative cosine 7x. You have to do your u sub, let u equal 7x, and have du be 7 dx. So you put in your 7, you put in your 1/7, and you've got 1/7 of the integral 7 dx becomes your du, and the sine 7x becomes sine u. So you get 1/7 times negative cosine u plus your constant, or negative 1/7 cosine 7x plus your constant. Everybody good there?
Yeah.
These are the simple u subs that I was hoping you'd all be able to do in your head by the end of the year. So hopefully you're doing some of these simple ones in your head. A couple of important u subs that you can either know or just memorize are the ones for cotangent of x and the integral tangent of x. Right, so if you want, you can just memorize these integrals because they show up often enough that it might be helpful. But just know that if you don't memorize them, they can be rewritten in terms of cosine and sine. So for cotangent, cosine over sine with u equal to sine x, and then du equal to cosine x dx, making this an integral of du over u, or natural log absolute value u plus your constant. And really similarly over here, sine x over cosine x, and then you'd let u equal cosine x. So du would be negative sine x dx. You'd put in your negative and your negative, and you'd get the opposite of the integral of du over u, which would then become negative natural log absolute value cosine x plus your constant. And every once in a while in the multiple choice, they might give you one of these integrals and just ask you what it is. So if you just know it, life is good. One thing to note about the integral for tangent, this is one form of it, but another form of it that is often written as the natural log of the absolute value, not a negative sign, it's just natural log of the absolute value of secant x plus a constant. And that just comes from doing the log rule, right? If you have a coefficient, -1 out in front, that can be brought in as a power. So cosine to the power of -1, not the inverse cosine, but cosine to the power of -1 is 1 over cosine, which is secant. So just be aware that the one for tangent is often written in both of those forms. So if you happen to come across that one in a multiple choice answer, those are the same thing. Everybody good there? I'll assume that's a yes.
Yes.
Okay. All right. Another one that we might end up seeing is something like this: x square root of 5 minus x squared dx. And so something like this, we want to take and u sub out the complicated piece of it, the thing that would be like in parentheses inside the other function that we have, square root 5 minus x squared. So we want to let u equal 5 minus x squared, so that du would become negative 2x dx. We'd put in our negative 2, and we'd put in a negative 1/2, and we'd end up with negative 1/2 of the integral of the square root of u. So I'm just going to write that as u to the 1/2 times du. So we'd have negative 1/2 times 2/3 u to the 3/2 plus your constant, or negative 1. Well, I guess we could make it negative 1/3, right? Half of 2/3 would be negative 1/3, and then our u is 5 minus x squared to the 3/2 plus the constant. Right. So those ones show up fairly often, and some years they put ones that are similar to that, but even a little bit more complicated, where they might throw in something like the integral of x cubed square root of x squared plus 1, let's say. So you end up with u equals x squared plus 1, and du is 2x dx. And then you note that you have an x cubed here rather than a 2x. So you can put in the 2 and the 1/2 and rewrite this as 1/2 the integral of 2x times x squared times u to the 1/2 dx. The 2x dx will become du. And we'll note that this other piece in here, x squared, can be found by just rearranging u equals x squared plus 1. So you'd end up with 1/2 the integral of u to the 1/2 times u minus 1 du. And from there, we would distribute this through 1/2 the integral of u to the 3/2 minus u to the 1/2 du. And from there, you'd integrate. I don't know if it's probably not super helpful to integrate that, right? 2/5 u to the 5/2 minus 2/3 u to the 3/2, and then you just plug your u back in. But just be aware that it's possible that you might need to figure out what some extra term that doesn't disappear with your u and your du, what that term might be equivalent to based on your original substitution. Everybody good with that there?
Yep.
All right, excellent. I had something as I was going through that problem. I thought of something I wanted to say. Now I just forgot it. Give me a second. Let me see if I can remember what I wanted to say about this. If not, it'll come to me later, I'm sure. Yeah, I don't know. I'm sure it'll come to me. All right, so that's the basic idea with your u substitutions. Anybody have any questions on the u subs for your integrals? All right, so that should sort of, take us to, that's everything we need to be able to do to integrate, right? Regular integration using the power rule, just all the rules on the formula sheet, and then all of the ideas of u substitution. That reminded me. I just thought of one thing, the thing that I was trying to remember earlier. Sometimes they might give you something like this, and I don't recall if we actually did any problems like this. And I'm going to do two different examples. One is easier and the other one is a little more complicated. So something like, I think we did do something like this. Something like x cubed plus x minus 5 over x squared, let's say, right? So if I wanted to integrate that, this looks like it's going to be difficult, but we should recognize that since there is just a singular term in this denominator here, I can divide each term by term, by the x squared and rewrite the integral. So x cubed over x squared is x. X over x squared is 1 over x. And then minus 5 over x squared is minus 5 over x squared. Everybody good with that?
Yep.
Okay. And then we integrate, right? X squared over 2 plus this one is natural log absolute value x. And then this is the integral of 5x to the negative 2, right? So that goes up to negative 1 and you divide by negative 1. So that'll cancel that out. So plus 5 over x plus your constant. I think we did do something like that. Hopefully we did. So if you just do this singular term down here, you can divide. Now, another thing that could potentially pop up, and I've seen this only a couple of times, but I want to make sure we've done it. This one, I'm not sure if we did. Something like x cubed plus 2x squared minus x plus 1 divided by x minus 2, let's say. This one, we have an issue where we don't have just a single term down here, so I can't just easily simplify each of these things. But what we can do with these, and if this shows up, it'll probably show up in the multiple choice on like one question, you can still divide. And with any luck, y'all remember how to do long division with polynomials, as well as synthetic division. This one, you can use synthetic division, right? Because the term is x plus or minus some a value down here, right? And so I'm going to do it with synthetic division, but I'll also do it with long division just to show you guys. So remember that for synthetic division, take the thing you're dividing by, the a value. So in fact, what we should really say if it's x minus a, but it's okay if it's x plus some number. That just means that the a value is negative. We put the a value up in a box, and then we put the coefficients 1, 2, -1, and 1 going across. And we'll note that suppose I didn't have a 2x squared there, I would make this a 0. I wouldn't just go 1, -1, 1. I'd go 1, 0, -1, 1. Oh, we're going to keep it there. So we drop the 1 down. We multiply by the 2. Bring it to the next one. Drop the 2 down. Add them together. Multiply by the 2. Add these. Multiply. And add. And so that would tell us that this integral should turn into x squared. Since we started at x cubed, the next degree down would be x squared. So 1x squared plus 4x plus 7 plus 15 over x minus 2 dx. And now we should be able to integrate that. And we get x cubed over 3 plus 2x squared plus 7x. And then this one, when you do the simple u sub, ends up being plus 15 natural log absolute value x minus 2 plus your constant. Everybody good with that?
Yes.
Okay. Just to show the regular long division also, I'm gonna write that out. We had x cubed plus 2x squared plus x, no, minus x plus 1. And we were dividing that by x minus 2. So we think how many times is x, or x times what gives us x cubed? Well, that's x squared. Then we distribute x squared to the x squared to the -2, and then we subtract. So 2 minus -2 is 4. And we'll bring down the minus x, and x times 4x gives us 4x squared. So we get 4x squared minus 8x. Subtract -1 minus -8 is a positive 7x, and we'll bring down the 1. And x times 7 is 7x, and we end up with 7x minus 14. Subtract, and you get a remainder of 15, which is exactly how we got x squared plus 4x plus 7 plus 15 over x minus 2. Everybody good with the synthetic division? I mean, sorry, the long division.
Yeah.
All right, cool. Let's see here. No other real basic rules for integrals or any other things that might be tricky with integrals that you would expect to see on the AP test. So we'll move into talking just briefly about differential equations. So I'm not going to spend a lot of time with it because we did a lot of the free response questions with differential equations. But remember that the idea of a differential equation is for us just to be able to integrate it to find a function and to find all functions that satisfy that differential equation. So if I say dy dx equals, x squared minus x plus 1, well, then we integrate and we get y equals x cubed over 3 minus x squared over 2 plus x plus some constant. And there are an infinite number of equations that satisfy the derivative of y as x squared minus x plus 1. I can put any constant in over here. But as soon as we say that we have some initial condition, let's say that when x is 1, y is 2, then you need to solve for that constant. So you put in your 2, put in your 1, and you find out what your constant is. And so in this case, let's see, what does that come out to be? 3 halves minus 3/2 minus 1/3. Is that right? What's 3/2 minus 1/3? Should be 7/6. You guys agree with that?
Yes, I think so.
Oh, good. Okay. So that should be y equals x cubed over 3 minus x squared over 2 plus x plus 7/6. Right. And so this is just a basic differential equation where everything is in terms of x. There's nothing really different about that other than you integrate and then you take your initial condition and solve for the constant. But we do end up with what we call the separable differential equations, like I was mentioning a little bit earlier, where we have both x and y as part of the differential equation. And these are called separable because you have to separate the variables and get all the y's, so dy over y to the left side, and all the x's, x, dx to the right-hand side. Then you integrate both sides. This side we know is the rule natural log absolute value y. This one is x squared over 2 plus a constant. So they both get a constant, and we talked about it a bunch of times. I think that you don't need to write the plus c on both sides. You can just put it on one side because if I have a plus c on this side and this side, I can always just subtract 1 over and I still just have a constant. So let's suppose that let's say that when x was 1, y was 2, we need to find our constant. So we get natural log of 2 equals 1/2 plus c. And so our constant would be negative 1/2 plus ln 2. And we'd substitute that in. And shows up fairly commonly that you need to exponentiate both sides to get rid of the natural log. And we end up with absolute value y equals e to the x squared over 2 minus 1/2 plus ln 2. And you need to recognize that using power exponent rules, you can take the e to the ln 2 as a constant out in front. So 2e to the, I'm just going to write x squared minus 1 over 2 since they both have a denominator of 2. And then we have to decide, to clear off the absolute value, if we want a plus or a minus in front of that. So the way we decide is we go back to our initial condition and plug it in. So if I plug in 2, I get 2 equals either plus or minus 2e to the, when I plug in 1, that becomes 0 over 2. 0 over 2 is 0, e to the 0 is 1. So I get 2 equals plus or minus 2. Well, obviously then 2 equals positive 2. So I keep it as a positive 2e to the x squared minus 1 over 2. But if the initial condition was when x was 1, y was negative 2, then we'd have to choose the negative in front of it. Does that make sense to everybody?
Yes.
Great. So that's the basic idea of separable differential equations. I just want to make a note. I'm not going to go all the way through this one, but sometimes they will put in something like this, where it doesn't quite look like there's a good way to separate it right off the bat, but you need to recognize that e to the x minus y can be rewritten as e to the x over e to the y using exponent rules. In which case, then we can get e to the y dy equals e to the x dx, and then integrate and solve. Right? So sometimes they will do something like that where the variables are being added or subtracted in a power. And so just make sure that you're aware that those can be rewritten as a product or a quotient, and that then you can separate the variables. And what's the integral of e to the y?
E to the x and e to the y.
E to the y, and the integral of e to the x should be e to the x plus our constant. And I didn't give you a value, so whatever. That's, suppose I said that it went through 0, 1. I don't know. That would tell us that e equals 1 plus c, and our constant is e minus 1. So we'd have e to the y equals e to the x plus e minus 1. And we take the natural log of both sides. And another common thing that I've seen is sometimes when solving differential equations, because a lot of the time you end up getting natural log of absolute value when you integrate, if you end up having to take the natural log of something as you're solving for y, don't just go and make it absolute values there. That's not how natural log works. It doesn't need to be absolute values. It's only the absolute value if you are integrating dy over y or dx over x or du over u or what have you. Good?
Yep.
All right. Now, the only little basic application that we did of differential equations was dy dt equals k times y. And this differential equation is saying that the amount of y, sorry, that's not what it's saying. It's saying that the rate of change of y, started off with the ending part, the rate of change of y is proportional based on this constant of proportion k to the amount of y. So when I have, more y, more whatever y represents, this thing is either increasing or decreasing more rapidly. The less of it I have, the less quickly it's decreasing or increasing. Okay? And we should know how to solve this differential equation, but we should also just know that this comes out to be exponential growth or decay. Right? Anytime you see dy dt equals ky, not kt, if it was kt, it's not exponential growth or decay. It has to be the same variable that's up in the numerator. Those have to match up. Then it's exponential growth or decay. Growth if k is positive, decay if k is negative. And we know that we could separate the variables on this. Dy over y equals k dt. And we integrate natural log absolute value y equals kt plus a constant. And we go through all the work for this by plugging in an initial condition. But we should know that this ends up being y equals y naught e to the kt, which is your basic exponential growth and decay formula. Like I said, growth when k is positive and decay when k was negative. Good or no?
Good.
All right, so be ready for like one question in the multiple choice, most likely, where they give you some sort of differential equation. They may just give you this base form without even giving you a k value and ask you what kind of growth does this model represent, and you'd say it's exponential growth. Or they might, give you this and say when there's 17 rabbits in the classroom, after a week or something, after some time period, figure out how many there would be after 3 weeks or something. So you just figure out what the k is, and then you plug in your values that you're looking for. And it should be pretty straightforward. But just know that these two things match up with each other. Dy dt equals ky and y equals y naught e to the kt. Everybody good with that? Any questions on that? And every once in a while, they'll ask a question in the multiple choice that says something like, they'll say, which of these, which differential equation is, I don't know, quadratic growth or something like that. Or they might ask which one is exponential growth, or they might ask which one is linear growth, or they might ask any sort of things. And so I'm going to put a couple different differential equations here. Dy dt equals k, dy dt equals kt, dy dt equals ky, dy dt equals k t squared. And so we should be able to determine which of these different things model each type of growth just by integrating each piece. So if I integrate this, I end up with y equals kt plus a constant. Well, what is kt? Is that quadratic growth? Is that exponential growth? Is that linear growth?
Linear?
Yeah, that one's just linear, right? Because this equation is linear. And you should recognize, you know, this one, ky, we just talked about, that one's the exponential growth one, right? And you should recognize this one. If I integrate this, what's that going to give me? That should be kt squared over 2. That would be quadratic growth, right? This one, when we integrate this, this would be cubic growth, right? Because you'd end up with kt cubed over 3 for y. So sometimes they'll put in a bunch of, like, you know, they'll write linear, quadratic, cubic, exponential growth, and they'll put some differential equation. And if they do that, all you got to do is integrate it and see which type of growth you end up with for the function y. Any questions on that? Everybody good with that?
Yep.
You're all good? Okay, cool. I think that's good for differential equations. Anybody have any questions on anything with differential equations and growth rates and all that?
Question, do we need to state the interval of validity, or do they not require that?
Not in the last 15 years in any pre-response questions have I seen them ask about the interval of validity or the domain of, or the domain restrictions on the solution to a differential equation. So I am banking on them not doing that. There's always the small possibility that they could. So if they do, just make sure that they're, we can do one. We'll do one like that real quick just to make sure. Suppose we have something like dy dt equals, I don't know, let's go with secant squared t plus t minus 1, right? And so that would give us y equals integral of secant squared, which is tangent, integral of t, which is t squared over 2, integral of 1, which is minus t, plus some constant. And they might have given us an initial condition that when, you know, when t was 0, the y value was 3 or something. So we'd have 3 equals 0 plus 0 minus 0 plus c. We get the function y equals tangent t plus t squared over 2 minus t plus 3. And we would then have to choose the piece of this function that is continuous and includes our initial condition. So tangent gives you a bunch of vertical asymptotes, right? It gives you vertical asymptotes, or not x, but t. T cannot be positive or negative pi over 2 times any integer, right? Because that gives you asymptotes. So you have to pick, if they do ask for the domain restriction or the interval of validity, you do have to pick the single piece of the domain of this function that includes your initial condition. So in this case, it needs to include 0. So that would be from negative pi over 2 to pi over 2. But like I said, the chances of them asking that, I have not seen it on any of the differential equation FRQs in at least 15 years of looking back through them. I think the last time, and I think it was even more than that, I think the last time I saw one was like 2003 or something like that from one of the FRQs where they asked for the domain. So chances are you won't have to worry about it, but good to be aware. Good. Any other questions on differential equations? All right. So next up is some of our applications of integration. So starting with a little bit more of the area. We talked a little bit about the area stuff, but we'll continue talking about the area stuff just a bit. So if we have two different curves, f and G, and we want the area between those two curves, okay, from A to B. All we have to do is integrate from A to B, f of x minus g of x dx. Easy enough. Top function minus bottom function. It does not matter if f is above the x-axis and g is below the x-axis, same formula, right? I know when we're talking specifically just about area, it does, but when we're talking about area between curves, it does not. If f crosses through partway through and g also crosses through partway through, right? And I want to go from, let's say, from A to B here. F and G, same thing. Doesn't matter that they cross through the x-axis on the interval. This formula will work 100% of the time. So all you gotta do is subtract the two functions and integrate from A to B. We can also find our area by integrating in terms of y. So if I gave you, let's say, y equals x squared, and we said from, let's say, from x equals 0 to x equals 2, so it's 2 here, but we were actually looking for this area, right? So the area between the y-axis and the curve. That says curve. From x equals 0 to x equals 2. This can be done in terms of y. We just need to rewrite y equals x squared as x equals root y. And we will integrate root y, or y to the 1/2, from the lowest y value of the region, which is 0, to the highest y value of the region, which if x is 2, y is 4. So we should be able to integrate in terms of y. This should give us 2/3 y to the 3/2 from 0 to 4. And a lot of people have had trouble in the past with finding the power of 3/2 or 5/2 at different x values or y values in this case. And my suggestion is always do the root part first. So the square root of 4 is 2. And then 2 cubed gives you 8. So this becomes 16/3 minus, well, 0 to any power is 0. And you end up with 16/3 as your final answer. Good or no?
Good.
All right. You can also find the area between two curves, doing it in terms of y. So suppose I gave you the function, let's go with the natural log of x, and I gave you, I don't know, we'll call that y equals negative 1/2 x plus 6. It doesn't really matter. Negative 1/2 x plus 6. That works. We can find the area of this region that is between those and the x-axis, this region right here, fairly easily. We'll have to use a calculator to find the points of intersection, but we can take the rightmost function for the region. So this is this function, negative 1/2 x plus 6 is the right portion of the region, and natural log of x is the left portion of the region. And we can do the rightmost function minus the leftmost function, and then integrate in terms of y. And so our lowest y value is 0, and our highest y value is whatever that intersection point is, which you should be able to find on your graphing calculator. And then we'd have to convert both of these. So this would become y minus 6 equals negative 1/2 x. So we need to multiply that by negative 2. So we'd end up with negative 2y plus 12 equals x. And this one would become, you'd exponentiate, you get x equals e to the y. So you'd integrate negative 2y plus 12, because that one's the rightmost function. It has larger x values, minus e to the y. That's the leftmost function because it has smaller x values. And so that would be our integral. And I don't know what that intersection point is, but your calculator would figure that out for you. This one would be a little bit more difficult if you wanted to do it in terms of x, because the upper function switches from natural log to negative 1/2 x plus 6 partway through the interval. So you'd have to write this as two different integrals. One from, this is 1 where natural log intersects the x-axis. You do 1 to the intersection point of ln x, and then you do the intersection point to, I guess that that should come out to be what, negative 6, so 12 is where that hits, right? So that's 12. So then you'd integrate from the intersection point to 12 of negative 1/2 x plus 6. Does that make sense how to do it in terms of y from right to left?
Yes.
All right. Any questions? What?
I had a question about the last problem.
Oh, okay.
So if you were trying to find the area on the other side of the curve, between the x-axis or the y-axis and the left side of the function.
The other side of the curve, like over here?
Yeah, then you would do x equals the negative square root of y, right?
That is correct. Yep, you would do
And
the
then-
opposite of the square root of y.
Would it also be a negative integral? Like you'd put a negative outside the integral too?
Only if you were asked for the area. If you were looking for the, if you're asked for the area should always come out to be positive. So you'd be integrating the negative square root of y. And so that will come out to be a negative value. So you gotta take the opposite of that integral. Yes, that's correct.
Okay, cool.
But you'd note that immediately those negatives could just cancel out.
Oh yeah.
Right, and then you'd just be integrating square root of y again from 0 to 4, which would be fine to do anyway, because you should know that y equals x squared is symmetric across the y-axis, and so you should be able to just, equate those two pieces as the same anyway. But yeah, this would be the original setup, and then you'd just say, oh well, that's just 0 to 4 of root y dy.
Okay, thanks.
Yep. Anybody else? Any other questions on anything so far before we get into volume? All right. So we had a couple different ways that we were looking at volume stuff. The first way that we were looking at volume was when we were talking about cross sections, right? The cross sections are specific shapes, let's say. So I might have something where y equals, y equals the square root of x from x equals 0 to 4, right, is the base of a region. And the cross sections perpendicular to the x-axis, we'll just make this easy to start with, are squares. Okay. And we want to find the volume. Well, that just means that cross sections perpendicular to the x-axis are squares sticking out of this region straight at you. So you just got a bunch of squares here. And so what we learned is that all we have to do is find the generic area of one of those squares. Right? The area of a square is just the side length squared. And so we figure out that the side length for each of these, s, is just y, or just root x. So that would tell us that the area is just y squared, or just root x squared, or just x. So the area of each of those squares that we draw is simply x. And so then we would integrate the 0 to 4 of x dx, and that would tell us that volume. Does that make sense to everybody?
Yeah.
Great. What does that come out to be? 8? Right. Now, putting a square in there makes life pretty easy. Sometimes they like to do that. Sometimes they make it a little more difficult. They might say that there's a rectangle where the length is twice the region stretching across. Like if I had that, if I had my function here, and these were y, then this would be 2y. So your area would be 2y squared. You would just have to rewrite the formula. Since we knew that y was root x, this would just become 2x eventually. Or we might have something, they might make it even more difficult. They might say, all right, let's suppose we had cross sections that were semicircles. That does not look like a semicircle. That looks better. So if the cross sections are semicircles, this is where people sometimes screw up. Because they do all right, and they say, all right, the area of the semicircle is 1/2 pi r squared, right? That's pretty straightforward. But the diameter of that semicircle is y. And a lot of times people make the radius of that semicircle y, and that's not correct. The diameter is y, which tells us that the radius should be half of y. Right? And so when we plug that in, we end up with area equals 1/2 pi times 1/2 y squared, or in this case, 1/8 pi y squared. And then since we're doing them in terms of x, if this was y equals the square root of x still, we just plug that in. Does that make sense to everybody? All right, and then the another shape that they sometimes like to use, not as often, but they like to use, I'm just going to draw some random region up here now, is quarter circles. And so if they do quarter circles, note that the radius is equal to y, right? This is y. That's the radius of that quarter circle. So you'd have 1/4 pi r squared. So just make sure you draw the picture and make sure you're real careful if they're using pieces of circles as the cross sections. Also in the free response, sometimes they might say something like the area, they may just give you the area of the cross section. So they may just say, let's use the function y equals, I don't know, e to the x from x equals 0 to x equals 1. And they might say that cross sections, this is the base, and the cross sections perpendicular to the x-axis have area of, they might just put something in there like 2 minus x squared, right? And so all you'd have to do is say, well, here's my function y equals e to the x from 0 to 1. That's the base of the region. And then we would say that the area of each cross section is just 2 minus x squared. So all we have to integrate is 2 minus x squared dx from, and since we're doing x values here, we'll just go from 0 to 1. Good or no?
Wait, so you don't have to relate y equals e to the x to like the area function?
No, because all they said is that the cross sections perpendicular to the x-axis have an area of 2 minus x squared. There should be something in there, huh? This is y equals e to the x from x to the, yeah, that's what I put up there, huh? Yeah, I mean, if that's all they say, then that's it. Suppose they said something like have area of 2 minus x squared times f of x. That's more likely what they do. Then they put in e to the x, something like that. They wouldn't necessarily put in just the 2 minus x squared, something like that. But yeah, if they just said the area is 2 minus x squared, then yep. Yeah, if they just did this. I have seen this too. There's nothing related to the e to the x, and that's fine. Right? It has nothing to do with it because the area of each cross section is only this. It's just this, no matter what. No matter how high up this, how wide this region is. So the wider the region is, the smaller the area is going. The larger the x value you get, the smaller this region is going to be. Does that make sense? It doesn't really. It's not affected by this. It's only affected by the x, and that's okay. It's not common, but I've seen that a couple of times in like word problems on the free response where they just put it in as simply 2 minus x squared, and they might do 2 minus x squared times the function, or they might do, I think the one I saw was about. I'm trying to think. It was about a lake. I think it was like an oil slick building up in a lake, and it said that no matter what the area of it, the area of the cross section was like 2 minus x or something like that. And so yeah, it's just an integral from a to b of whatever they tell you the area is, which makes it easier. But yeah, it does not relate to the e to the x at all because that's the area is not related to it. It's specifically this area. It's a little counterintuitive because they give you this function, but that is correct. Does that make sense or no?
Yep, thank you.
All right. Let's see. We could also do cross sections perpendicular to the y-axis. So that's a good thing for us to briefly talk about. Oftentimes they like to do those using like a circle or something like that, but not necessarily always. They might say, let's say we had this. We'll just say we have y equals x squared. And we'll say that we are having cross sections just perpendicular to the y-axis. We'll just make our lives easier. We'll just say they are squares with, they're just squares. We'll say from y equals 0 to y equals 4. Okay, and so stretching across y equals x squared from y equals 0 to y equals 4. So these squares, each of these different squares that we could draw inside of here, right? They all have an area, once again, of the side squared. And the side length is this distance from here to here is just x. So s is equal to 2x. And so we should be able to go in and say, well, if s is 2x, then the area is 4x squared. But since we know that they're perpendicular to the y-axis and we're going from y equals 0 to y equals 4, we've got to convert 4x squared into terms of y. So 4x squared should just be 4y. And so we will integrate from 0 to 4 of 4y dy. And you integrate and solve. Good or no?
Good.
Okay, so that's the other thing, is doing them in terms of y. Less often that they show up in terms of y, but sometimes they do. Cool. All right. Then what we did next was we talked about taking some random region f of x and revolving it around the x-axis, right? So that we end up with cross sections that when you slice them vertically are circles, right? We end up with a circular cross section. Okay, one second, we'll talk about this in a second. So Alex just asked me about the formula for equilateral triangles. So yeah, that's another shape. They give you the area, if they say the cross sections are equilateral triangles, the area of an equilateral triangle, just so that you have it, is side squared root 3 over 4. So that's a good one. That's another one that they commonly put in there. They also will sometimes do isosceles right triangles. If they do an isosceles right triangle and one of the legs is stretching across the region, then that's easy. That's 1/2 base times height. If they have the hypotenuse stretching across the region, right? So if this is isosceles and it's a right triangle, but the hypotenuse is stretching across the region, then you've got to recognize that this is a 45, 45, 90 right triangle, and that side lengths are 1, 1, and root 2. And so you should be able to find the, you should be able to figure out what the base and the height of this are, so you can cut this down, right? And so this is root 2, this is root 2 over 2, and what should this little piece here be? This should just become another 45, 45, 90, so this is another root 2 over 2. And so you'd see that it's 1/2 of root 2 over 2 times root 2 over 2, which should be, what does that come out to be? 1/4. Right, so that area should just be 1/4 of whatever this thing is there, right? So suppose this is, this is, let's say this is your x, say root 2 is x, then this should be, you should be able to plug it in and figure out what that is. But just use the right triangle trig to figure it out. Make life easy for yourself. But yeah, this one is the most common if they talk about triangles, that they want you to do an equilateral triangle. Or an isosceles right triangle, but isosceles right triangle where one base is, or one leg is the thing stretching across the base. All right, so when we revolve around an axis, an x-axis or a y-axis or any other horizontal or vertical line, we end up getting these circular cross sections. And so we know that the circular cross sections have an area of pi r squared. And so all we had to do was figure out what the radius was. And if we're going around the x-axis and it's just one simple function, your radius should be just your function, or should just be y equals f of x. And all we do then is we integrate from a to b, the pi out in front, times your radius, which in this case, like we said, was f of x, squared dx. Good or no?
Good.
Good. So that's if the region is fully pushed up against the x-axis. Sometimes you might have a region that is not fully pushed up against the x-axis that you want to revolve around. So you might have f and g, and you're going from a to b, taking this region, and we might want to be revolving that around, right? Get whatever we get down there, right? And so in that case, since the region is not fully pushed up against the axis that you're revolving around, you're going to do pi times the outer radius squared minus pi times the inner radius squared. And your outer radius is just the upper function, and your inner radius, a different color, your inner radius is just your lower function. So you do pi times the outer radius squared minus pi times the inner radius squared, and integrate from a to b. Conceptually okay with that, everybody, or no?
Yep.
Excellent. Okay. right. Okay. We also might want to do this around, we'll talk all horizontal lines first, then we'll move over to vertical lines. We might need to revolve something around, let's say y equals f of x. And we want to revolve it around the line, the section between that and the x-axis, and we want to revolve it around the line y equals -1. Well, it's the same concept. The same thing's going to apply, except we're going to have an outer radius and we're going to have an inner radius. So the outer radius is the distance from the function to -1. Well, this is f and this is 1. So your outer radius ought to be 1 plus f of x. Your inner radius is just 1. That doesn't change. And so you would do pi times the integral from a to b of your outer radius squared minus your inner radius squared dx. Good or no?
Good.
Great. Now, if we were to try and take this function, this section right here from a to b, but revolve it around something that was above that region, we'd have to be careful and note that our outer radius is now 4, and our inner radius has to be the full 4 minus that f of x. So outer radius is 4, inner radius is 4 minus f of x. So we have pi times the integral from a to b of 16 minus 4 minus f of x squared dx. Everybody good with that?
Yeah.
Wonderful. Anybody, any questions?
So on population density problems, the population density would be dx, and then you just put whatever shape they give you onto a graph and then find the area.
Population density problems. It sort of depends on how it's worded, but let's see, population density, yeah, they'd probably give you that as your dx most likely. Do you have a specific problem you were looking at?
I think it was 2008. They had one about a city.
Okay, let me
Find the-
give me 1 second. 2008, you think? I can try and pull it
Yeah.
just so I can. It was free response, I assume.
I think it was multiple choice.
That was multiple choice. Yeah, I don't see it in the 2008 free
What was
response.
the 45, I think, on multiple choice.
Okay. Just trying to pull it up on my phone. Oh, I put that one into Google Drive, right? So that one's a released one. I can get that on the Google Drive on my phone, so I don't have to mess with it on my laptop. 1 second here, let me find it. 2008, there we go. 45, you said?
Yeah.
Okay, yes, this city. So yeah, let me just throw this one up here and we'll talk about it real quick. So let's see, what are they got? They got a river over here. They got a 4-mile wide section here. This is 7 miles. This is your city. And then they said the app just shut off my phone. Give me a second, sorry. Okay, sorry, I'm back into it now. Okay, so then it asked, the population density. So it says the density of the city at any point along a strip X miles from the river's edge. So our density is like changing as we go this direction, right? As we go from left to right, the density changes with each strip. Changes as we left to right. I spelled hard. There we go. Left to right. Is f of x. So they're saying that the density is f of x, not dx, but they're saying that each strip has a thickness of dx. That is correct, if that's what you meant. And so they gave you a bunch of different expressions to represent the population of the city. The right one there should be, it looks like it should be choice B, because they want the total population, and the population should be the density times the area of whatever the section that we know that density of. So your density is f of x, and the area of each little section of each strip of land that has a separate density is that dx, that small dx, times a width of 7. So we should have a 7 in there, and we should have a dx in there, and we should be integrating from 0 to 4. So I don't know, does that answer your question or no?
Yeah.
Are you sure? You're sure that you sounded not quite sure still, so you're good?
So dx, so the area of each section is kind of like coming out of the.
So the area, so think about it this way. So here are your strips of land with whatever densities that they might have, right? And imagine that there's an infinite number of these, because every instant or every tiny fraction of a mile that you move from left to right, the density is changing, is what it says, right? Changing based on this function f of x. So to find the density, or to find the total population, you need to take the density, because the density is, I'm going to do this, the density would be people divided by square miles, right? That's what a density would be, number of people in a certain area. And so if we take the density and we multiply it by the number of square miles, that ought to give you the total number of people. True?
Yeah.
Okay, so that's what we've done here. We've said that the density, which is f of x, times the area of each of these strips, which these are infinitesimally thin strips of a width dx, and then have a length of 7. So our area is 7 dx, and our density is f of x. Right, these match up. Area is 7 dx, 7 for the length times the width of the rectangle is dx. And then the density is f of x, multiply those together, 7 f of x dx, and integrate across all of your x values from 0 to 4.
Okay. Got
Does
it.
that make more sense now?
Yeah.
All right, wonderful. Yeah, if what I say at first doesn't make sense, don't tell me it makes sense. It's okay. Because if it doesn't make sense to you, it probably doesn't make sense to the other people also that are trying to listen. So it's okay if it doesn't make sense. It will eventually. Everybody good with that now? Okay. All right. Let's see here. I forgot sort of. Oh, we were doing the volume stuff, right? And we just did the x-axis stuff. So we need to do the y-axis stuff, right? So we can do the same thing with all of our volume by revolving, let's say, around the y-axis. So if I have a function like y equals x squared, and I want to take the region between that and the y-axis and revolve it around the y-axis, since in this case we would be slicing horizontally, we're going to have to do everything in terms of y. Yeah, Krista, I'll go over shells also once we finish all the what do you call it, discs and washers. I'll go over shells also. So in this case, since we're going to slice horizontally, it's going to be done in terms of y, like I said, dy, and we will just need to find the radius. Well, that radius is just whatever distance x I've gone over. Right? Radius is x, but I need the radius to be in terms of y, so we need to let x equal root y. So our radius is going to be root y, and we would integrate root y squared dy times our pi from a lower limit of 0 to an upper limit of whatever, I might have, whatever I set up here, we'll just say up to y equals 4. And so we integrate from 0 to 4. Does that make sense to everybody?
Mm-hmm.
Okay. Now we might end up with, and it's less common that they do this, but you might end up with something that is, let's see, let's come up with a good function here. Something like, suppose we had y equals x squared, and we had y equals 2x squared. And both of those are parabolas, but we're going to take the region between them from y equals 0 to y equals 4, and we're going to take that and revolve it around the y-axis. And so if we were to do that, we're going to end up with a couple of pieces out here. We're going to end up with this like 3-dimensional little, I don't know, bowl-looking type thing here. Slicing it horizontally, we do it in terms of y, and we'd have to find our outer radius and our inner radius. And our outer radius would just be the x from 2x squared, and our inner radius would just be the x from x squared, all in terms of y. So this one we already just did was root y. This one, right, if we're looking at y equals 2x squared, well, then that would just be the square root of y over 2. And so we set it up as pi times our outer radius squared minus our inner radius squared dy from whatever your limits happen to be that I gave you. Everybody good with that?
Yep.
All right, excellent. Let's see here. And we might also need to take something and revolve it around a different vertical line. So we might have something like, we'll just keep using y equals x squared just because it's easy there. Y equals x squared, this region right here, but we're going to revolve it around x equals -2. So now we're going to have an outer radius. That outer radius should be 2 units plus whatever this x value is, whereas our inner radius should just be 2. And so it should be pi times our outer radius of 2 plus x, which is really 2 plus root y, because it has to be done in terms of y, because we're going around a vertical line. So 2 plus root y squared minus 2 squared dy, and then you integrate from whatever your limits of integration were in terms of y. Everybody good with that?
Mm-hmm.
And if we wanted to revolve the same region, this region right here again, around some line like x equals 5, well, then we would note that our outer radius would be 5, and our inner radius would be the entire distance of 5 minus however far x we've gone over, which would be 5 minus that root y. So we'd have 5 squared minus 5 minus root y squared dy with a pi out in front. integrated from wherever our lowest to our highest y values of the region I gave you. Good?
Yes.
All right, that's about it for volume using disks and washers. Of course, it's super likely that you're going to see these either in the calculator or the non-calculator free response. A lot of times in the non-calculator ones, they will just ask you to write out the integral and not solve it, but make sure you read and see if it says that. Don't just immediately say, I'm not going to solve it, because it may be one that they do ask you to solve. And then on the calculator section, all you need to be able to do is set it up and then punch it into your calculator correctly, using math 9 on your graphing calculator, which I hope that we don't need to practice. We should all be good with that. Okay.
Yeah.
All right. So, so somebody's asking about shells. So I'm going to do a quick little thing here with shells. Even though shells are not required for the AP test, every few years there is a problem in the free response where using shells might make your life a little bit easier. It might mean that you don't have to convert from one variable to the other or something like that. So as far as shells go, the idea is that we are looking at these very thin, hollow cylinders, right? Like a toilet paper roll or something like that. And so in order to find the volume of one of those, it's the circumference, 2 pi r, times the height, so 2 pi r h, which that gives us the lateral surface area. And then we just multiply it by the thickness, which, well, in this case is a dx. And the way we know if it's dx or dy is, suppose we were revolving, we were revolving around a vertical line here. So we would sketch what we call a typical rectangle, and that's what we're sort of revolving around here to get these cylinders. And since it's parallel to this vertical line, it has a very infinitesimally thin thickness in the x direction. And so the good thing about shells is that it will allow you, if you are revolving around a vertical axis, to complete the problem in terms of x, rather than disks and washers, which if you're revolving around a vertical axis, will require you to do the problem in terms of y. And so if the function, like this one that we'll talk about, this simple one here, this problem that we were originally working through, right, we had to convert from x to y, which wasn't a big deal because it was an easy function. But if we'd done it using shells, we wouldn't have to convert out of terms of x. So let's take a look at that one real quick. Suppose we had y equals x squared. I think we did from y equals 0 to y equals 4, I believe. And if y equals 4 on y equals x squared, then that would be going to an x value of 2. And so we would, since we're going to go around the y-axis, we would sketch any typical rectangle in that region and revolve it around. And then we just figure out what all those things were, what the radius and the height and the thickness were for this particular cylinder. So it's 2 pi integrated from x equals 0 to x equals 2 times our radius. And anytime you revolve around the y-axis and you're doing shells, your radius will always just be the x value that you've run over, so x. And then your height, in this case, is 4, is the full height of this thing at the highest point, right? It's 4 minus however far up we've gone away from the x-axis. So our height is 4 minus y. And like we said, we got to do it in terms of x, which is great because this is written in terms of x. This is 4 minus x squared. And so you would integrate this. And you'd find that if you did this, 2 pi times the integral from 0 to 2 of 4x minus x cubed, you'd get 2 pi times 2x squared minus x to the 4th over 4 from 0 to 2, which would be 2 pi. And you plug in your 2, you'd get 8 minus 4 for the 2, and then you plug in the 0 and you get 0, and you'd end up getting 8 pi, which if we look back, oh, we didn't actually do that one. Well, if we looked back and did this one, we had pi times the integral of y from 0 to 4, which would be pi times y squared over 2 from 0 to 4, which would be also 8 pi. So it works out exactly the same. Oh, this density somehow got thrown in the wrong place. Where were we talking about the density? Put that in the right spot. That's better. Okay. Does that make sense on the shells there, Krista?
Yeah, thank you.
Yeah. Do you want me to do? I mean, I'm happy to do some more of them, like revolving around other like the x-axis or other lines. But if you think you're good with it or just that, that's fine, since it's not going to be required. But I'm happy to do more if you want.
I'm okay, but I do have a quick question.
Okay.
How many optimization and related rates problems do you typically see on the test?
I would expect to see one of each, at least, maybe two of one or the other in the multiple choice,
Uh-huh.
and potentially one part of one of the free response questions on each of them is my
Okay.
best guess. There won't be a ton. It's not like, it's not predominantly optimization related rates. They just, yeah. In some years, they don't put it in the free response at all, and they might put a couple in the multiple choice instead. But I wouldn't guess more than 5 total parts of questions are optimization or related rates throughout the entire exam.
Okay, thank you.
And when I say optimization, I'm meaning like optimization in terms of like a word problem optimization, not just like, find the max of the min, because those are technically optimizations also. Those there's going to be more of like finding the max of some function or the min of some function. But that, I assume you meant like word problem type optimization, right?
Yeah.
Okay. All right. Anybody else have any other questions? That is the class in 3.5 hours between last review session and this review session. Anybody have any specific questions or anything you'd like me to go through a little bit more before I start looking at some problems that I think would be good for us to take a brief look at?
How would you do shells for like the washers, like the donut volume sort of questions?
So, sorry, say that again. How
would
would
you
you do them?
Yeah, how would you use the shells method for like donut cross sections?
The exact same way. Oh, and yeah, I'll show one in a second. Yeah, damn, I forgot I was going to go over fundamental theorem of calculus. I said that last time that we would do it today, so we're going to do that right now also. And also multiple choice involves slope fields. Yeah, yep, yeah. All you people that ask for specific things, I will do those right after I talk about this shell thing here. So let's go back to this one, right? This is one that we did using discs and washers, but it was like had the gap in between. So like, are you talking about something like this? Yeah.
Yeah.
Okay. So let me just get a new page down here. So we had x squared, we had 2x squared, and we're going around the y-axis. And so if we wanted to do shells with this, it's the same basic concept. We're going to go, this is our region. Let's say here this y equals 4 was our highest point. It's the one we did before. Well, it's a little bit different here in this case. But this one's kind of annoying. We'd have to split this one up since we're doing it in terms of x. Like we're doing this one with shells around the y-axis, right? We have to split this into 2, which makes this one a little bit irritating, right? Because since we're doing it in terms of x, we have to look at upper function minus lower function. Well, from x equals 0 to x equals 2, right, where this ends up hitting y equals 4, the upper function is x squared, and the lower function is 2x squared. So your height from 0 to 2 is x squared minus 2x squared. But your height from 2 to, what is that? What is the x value there? If y is 4, that's the square root of, right, if y is 4, that's, why am I not able to do basic algebra at the moment?
Shouldn't the function that's further to the right be a half of x squared?
Yeah, it should be a half of x squared. That's why that wasn't making any sense to me. Did I do that one as 2x squared, or did I write those correctly the first time? I wrote those
I
incorrect.
think you did it incorrectly the first time too, yeah.
Oh man, all right, we'll pretend that's a 1/2 there. Oh man, why did I do that? I don't know why I did that. So this would have been a 2y. That's bad. How come nobody said anything to me about that?
We cannot do basic math.
If you guys tell me if I'm doing something stupid, you got to tell me I'm doing something stupid. All right, now that makes more sense. All right, so in this case, as we're going from x equals 0 to x equals 2, it's x squared minus 1/2 x squared. But then from 2 to now this should be to 2 root 2. The height is the upper function, which is 4, minus this 1/2 x squared. And so you just have to do two different intervals, one from 0 to 2 with this height, one from 2 to 2 root 2 with this height. The radius for both of them would still just be x, and your thickness would still be dx for both of them, because each rectangle would be thin in the x direction, but you have to split it right here. And that's not always the case, that just happens to be for that region that I drew. So even if there was a gap and the upper function was always the same as the lower function, I mean, the upper function and the lower function were always the same on the entire region, then that's fine. All that would happen is, like, let's say that's like the concept of, suppose we have something like, what's a good thing? Well, we'll just take a simple function. We'll just say y equals x squared, but we're going to say from x equals 1 to x equals 2. All right, so if I'm taking y equals x squared from x equals 1 to x equals 2, and taking that around the y-axis, I'll end up with like this sort of thing over here. It's like bowl-shaped until I have this big gap, right? There's nothing in here. There's no space there. And so the rectangles that I draw, you know, I'm only revolving rectangles around from 1 to 2. So I'm still going to get this big gap in the middle. The first rectangle I'll revolve around is this one, and then all the way to this one, every little one in the middle, but that still leaves me that hole in the middle. And so that's fine, as long as we just make sure that we integrate from 1 to 2, not from like 0 to 2 or something. Does that make sense?
Yep.
Are you sure?
Yeah, it does. Thank you.
The radius is x, and the height in this case would just be x squared. So yeah, you just plug all those in. All right, I'm just going to go down the line here with the questions that people are asking in the chat real quick. So 2013 AP test number 90. Okay. Let's see here. Let me pull that up on my phone real quick. 2013. Oops. Assignments. That one is in the Google Drive. What is it titled in the Google Drive? I don't see it in here.
Oh, isn't it just called like AP 2013?
Oh, there it is. Now it showed up. I don't know why it didn't show up before. Okay, yeah, AP calculated to that. Okay, number 90. All right, let me quickly scroll down to that. There it is. Okay, it's the differential equation, right? It says the population of a city grows according to dp dt equals kp. So we know that this is exponential. Right, this is exponential growth because it's dp dt equals a constant times p, which means that it should come out to be y equals y naught e to the kt, or p equals p naught e to the kt. Right, that's the solution to this differential equation. And it says if the population of the city doubles every 12 years, so we know that if we started an initial population, so let's say after 12 years, the population equals 2 times the initial population, because that's what it says. If the population of the city doubles every 12 years, what's the value of k? So you'll just go in and say 2p naught equals p naught e to the k times 12 years. And you'll just solve for k. So you can divide the p naught off of both sides, and you end up with 2 equals e to the 12k. You take the natural log of both sides, and your answer is k equals the natural log of 2 over 12, which is some decimal on there. I don't know which one of those it is, but natural log of, what's the natural log of 2? It's like 0.6 something or another. Divide that by 12. It's probably choice A. I don't know. That'd be my best guess. Either A or B. The others are all too big. 0.69. I think it's 0.693 is natural log of 2. So divided by 12 would probably be choice A. Yeah. Does that make sense? Yeah, Alex, yeah, you're good. Okay. Okay, and the next question somebody asked was multiple choice questions that involve sloped field. Did you have a particular one in mind? There aren't usually a ton of slope field multiple choice questions. So I'd have to flip through to find one. There's usually like one every 5 years.
Wait, if you want to skip to the next one, I can find a problem I did this morning on it and send it to you. It'll just take me a couple minutes.
Sure. And now let me see who asked me. Unless who asked me that? Oh, Allie. Did you have one in mind, Allie, or no? If not, it sounds like Cassie will find one for us. And then, is that good for you? Or do you have a specific one? Okay, one in 2015 that you want. Okay, let's look at that one. Do you know what number offhand? I can scroll through and find it. But 2015. I'm guessing it was in the. Oh, there it is. This is number 8. Yeah. Okay. Give me 1 second here. Let me, because there's like, it's not one of like the simple basic slope fields. So I don't want to have to try and draw that thing. So let me just clip it off of my laptop and throw it into the thing there so everybody can see it. Assignment 2015. What number did we say it was? Number 8, right? Computer. I would like a district laptop to really work quickly. Oh, geez, I've gone too far. There we go. Okay. So now I should be able to throw it in here. Okay, you guys can you guys see that? Is that in there now?
Yep.
Okay, cool. So we've got the slope field for y squared times 4 minus y squared. If y equals g of x is the solution to the differential equation, with the initial condition that g of -2 equals -1, we want the limit as x approaches infinity of g of x. So remember that the solution to a differential equation is just the curve that you would sketch if you went through that point. So we're going to go to the point -2, which would probably be about over there, and -1, which would be right about over there, probably. So somewhere right about there. And we're going to think about what these, what this curve would look like. And then what would happen as x went towards infinity of g of x. So this is asking us about, remember that a limit as x approaches infinity is a horizontal asymptote to the right. And so we're wondering, is there a horizontal asymptote to the right of this? And so if we were to look at all the different options here, if we sketch this curve through here, we might see, we're going to see that these slopes are going to become, when y is 0, these slopes are going to be 0. I can't go through that line, but something like that, right? And this will probably narrow out that way to there's probably some other ones in here that would flip out to the left there. But we'll note that we are going towards a slope of 0. And the only options that are given to us here are 2 and 3, and which would be up here, which, I mean, we're not going to a horizontal asymptote of 2 or 3 up here because we're going to flatten way out here and go right along the x-axis. So it's going to have to be 0 just because of the nature of this function having slopes of 0 all the way across here. So anytime you have a function with a slope field that's drawn, if for every y value, we're going to say for every y value, y value of 0, regardless of x, that tells us that that's a horizontal asymptote. And so if the y value of 0, if it equals 0, right, the slopes are all 0 there, then that's a horizontal asymptote. Same thing up here. Regardless of the x values, there is a horizontal asymptote up here of y equals 2, right? It just would have to be from some function that was up here that would end up coming down like this, or some function that started up here that went like this. So you might have a function in here that would work. You'd have functions like this that would work. And then you'd have, I don't know what's happening above there, but you could have a horizontal asymptote of y equals 2 if you were up here, because you'd be approaching all slopes of 0 on this horizontal line. And so the thing, does that make sense or no?
Yeah, thanks.
Yeah, and so the thing that we talked about, and I only talked about this briefly, was I said something to the effect of, if the slopes on the, and this sounds weird, if the slopes on the slope field in a line, this sounds really weird, but this is the best way I can think to say it. If the slopes on the slope field in a line match the slope of that line, it is a, I'll say it is an asymptote, right? And so that's what's happening here. The slopes of the line y equals 0, a slope of every line on y equals 0 matches a slope of 0. The slope of every line on y equals 2, right? This is the line y equals 2, has a slope of 0. And since the slopes are 0 on it, that's also a horizontal asymptote. Here, the line is y equals 0, which has a slope of 0, and all the slopes are 0. The same would be true if your slope field looked something like this, and we did it with like an oblique asymptote. This is the line y equals x. And, maybe we have some other things going on here, right? Who knows what these ones are doing? And they're all, they may all be weird over here doing whatever they're doing. But along y equals x, which has a slope of 1, all of the slopes there are 1. And so that would be an oblique asymptote. Does that make sense?
Yeah.
Okay. All right. So now, next thing, 2 people, actually the last thing that people have asked, which is probably good because we only got 10 minutes, and it'll probably take about 10 minutes, is questions about the fundamental theorem for calculus. So, and yeah, I forgot to go through this. I said I was going to today, but I forgot. So one more thing about the slope. What does the vertical line mean on the slope field? What vertical line?
Under the 3.
These? Those are not actually vertical. They're just, well, they could be. It's hard to say. I mean, those don't mean anything necessarily though. I think those are just super steep slopes that this gets really, really steep as it's up high. And as it comes down, it probably does like one of these as it approaches that asymptote. It's just super steep. But it's hard to say. They wouldn't ask you about something that far off on the edge of the graph. They'd ask you something more like, that's more in the center where the slopes are more varied. Okay, so the fundamental theorem of calculus. There's two parts to the fundamental theorem of calculus. One is the evaluation part. That's our definite integral thing. Evaluate it, the upper limit, evaluate the lower limit, and find the difference, and so on. That's the easy part. The part that people screw up, though, is the part of the fundamental theorem of calculus where we say that the derivative of the integral from a constant to a variable of some function, doesn't matter what the function is, and normally this is going to be like t squared or something, or some other function there, dt, is just that function in terms of x. That's the first part of the fundamental theorem of calculus. It says that the derivative and the integral are just inverse operations of each other, effectively. And so you can think about that for a function that's easy for us to integrate, like t squared. Right, well, what's the integral of t squared? It's t cubed over 3. So I'm going to put my derivative out in front. So I still have the derivative. I'm just doing the integral part. The integral of t squared is t cubed over 3. We're going to evaluate that from 2 to x. Right, and then we're going to take the derivative of that. So that becomes x cubed over 3 when I plug in the x, minus 8/3 when I plug in the 2. And then when I take the derivative of this, well, what's the derivative of 1/3 x cubed? It's x squared. And what's the derivative of minus 8/3? It's 0. Doesn't matter what this lower limit constant is, as long as it's a constant. When you take the derivative back of this, it goes away. So they might ask you, the easiest thing they might ask you using the fundamental theorem of calculus is something like this. What's the derivative of, the integral from 3 to x of sine of something like t squared dt, where you don't actually know how to integrate it, but you need to recognize that the fundamental theorem of calculus says that if I integrate from a constant to x, some function, and then I take its derivative, I just get that function. So that's the easiest possibility. That's the hope, right? But it gets more complicated because they might say something like, what's the derivative with respect to x of something like the integral from 5 to x squared? We'll just use sine of t squared again, right? Well, in this case, we integrate sine of t squared, which we actually can't integrate, to get some function, and then we would take its derivative. Well, when you do that, when you evaluate, and this is what I did in class, I said let capital F be an integral of sine of t squared. So just let some function capital F, we're going to pretend that capital F is the integral of sine t squared. So we're looking at the derivative of capital F, right? That's our integral of sine of t squared, evaluated at x squared, minus capital F, evaluated at 5. And the same thing goes on here. We say take the derivative of capital F. Well, the derivative of capital F should be sine of t squared. So I'm going to evaluate sine of t squared at x squared. And then minus this is sine of 5 squared. And then we're taking the derivative. Well, our derivative of that then ends up being the derivative of this thing times the derivative. It ends up being the sine of x to the 4th times the derivative of the x squared, right? And so we end up getting 2x times the sine of x to the 4th. So effectively, we can not worry about all of this. We're not going to worry about all of this stuff here. I don't know why I shouldn't have the derivative outside of there anymore. I should have the derivative of x squared outside of there. Because that's the chain rule. It says when we take the derivative of capital F of x squared, we get the derivative of capital F at x squared times the derivative of x squared. So 2x times sine of x to the 4th. And so effectively, all you've got to do, and I'll make another one up here, 3 to sine x of, squared dt. All you have to do is take this sine x, replace the t with it, and then multiply by the derivative of this sine x, right? So this becomes the sine of sine squared x times cosine x. Does that make sense to everybody or no?
Yes, it makes sense.
Okay. Now, it can get complicated in two different ways. One is if we have something like the derivative of the integral from 3x to x squared of sine of t squared dt. Because now this lower limit's not a constant. So what we have to do is we have to do the sine of our x squared, plugging in the x squared for t, and multiply that by the 2x, the derivative of x squared. And then we have to subtract, using the second part of the fundamental theorem of calculus, upper limit minus lower limit, the sine of 3x squared times the derivative of the 3x. So 3 sine 3x squared. And then you'd simplify all that to 2x sine of x to the 4th minus 3 sine of 9x squared. Does that make sense?
Yep.
Okay. And then the other way that this might show up is in the calculator multiple choice. They might say something like f of, let's see, how do they word these normally? They might say something like and we did a whole sheet on these. Something like this. Let's say they'd say like f of 3 is what we're trying to find. So we'd say like find f of 3 if f prime of x was some function that we don't know how to integrate. So we'll say something like what we've just been using, sine of x squared. So we'll just keep using that. So if f prime is sine of x squared and f of 1 is equal to 7. So we would say that capital F is an integral of f prime. And so we would say that when we integrate f prime, we should get capital F. Well, actually, let's write it this way. We'll say the integral of f prime of x dx from a constant to x with the derivative in front of it, right? Actually, what I need the derivative. So we'll just say this integral from the constant to x of f prime of x dx should be equal to capital F at x plus some constant, right? So we need to figure out what this constant is and what this constant is. And so effectively what we're doing is we're saying, since the initial condition we had is f of 1 equals 7, we're saying that the integral from 1 to x of the sine of whatever it was, t squared, plus some constant needs to equal 7. Because if I plug 1 in for x here, that gives me the integral from 1 to 1 of this function, which is 0. And we get 0 plus a constant equals 7, telling me that the constant is 7. So we can then say that f of x is equal to the integral from 1 to x of sine of t squared dt plus 7. And it asked us to find f of 3. So f of 3 on your calculator, you'd have to use your calculator, would be the integral from 1 to 3 of sine of t squared dt plus 7. Does that make sense to everybody?
Yeah.
Yeah, and so you'd use your calculator to evaluate and do that. So that's the other way that we'd use, these initial value type fundamental theorem of calculus type problems. It's in that assignment was called calculator initial value problems, And one of those seems to show up almost every year in the multiple choice. So if I were you, I'd go back and look at that assignment called Calculator Initial Value Problems between now and Tuesday, for those of you taking the Tuesday test. Any other questions? I got just a minute or two here, and I'm gonna go to my kids' baseball game. So,
Do we have to show the thing where it's like plus C equals 7, 0 plus C equals 7, or if we just skip it and just say plus 7? Because
you can just put +7. Yeah, I mean, it's normally that type of question is. I've never seen it in the pre-response. It's always in the multiple choice, so you don't gotta show anything.
got it. So whatever initial value they give us, just put that as your lower limit and like add it on.
Whatever X value that they initially give you is your lower limit. Whatever it equals is your constant at the end, and then use your calculator to evaluate.
I also had a question going back to derivatives. If you have a semicircle and then you're finding the derivative at the end point, it goes towards negative infinity, right? Or positive infinity, so it doesn't exist at the end point.
The derivative at the end point does not exist. No, you can have a derivative from since it's going towards an infinity or a negative infinity, even the left or the right hand derivative wouldn't exist also.
Okay, thanks.
Yep. Any other questions? And there'll be a chance on whatever it is, Monday, right? Monday night, I think, is your last review session with me. So if you think of something between now and then, you can ask on Monday also. Everybody's good.
One last question. So a function is only differentiable on like an open interval, right? It never use square brackets, only open brackets.
I mean, it can be differentiable on a closed interval also, but generally, like for all the theorems, for the theorems to be true, it only has to be differentiable on the open interval. But it can be differential on a closed interval too. That's fine. Other questions? Nobody else?